Welcome everybody for our weekly seminar series of today. Today we are hosting Dr. Juliana de Sousa Nogueira from the University of Sao Paulo in Brazil. Some information about Juliana. She has a PhD in geochemistry, and she is a researcher specializing in paleoclimatology and environmental studies. She has extensive expertise in conducting in situ studies, utilizing multi-proxy and multi-matrix analysis to investigate past climate variations. Additionally, Juliana employs remote sensing techniques, utilizing diverse satellite-derived products to enhance the robustness of climatic reconstructions and interpretations. Her research spans various environments, including the Amazon forest, Sahara Desert, Antarctic Peninsula, Carpathian Mountains, among others. Currently, Juliana is in Sao Paulo since 2 months ago. And she continues to contribute to resolution of real-world environmental and societal challenges by deepening the understanding of late Holocene and climate dynamics. So first of all, Juliana, thank you very much for joining us, even virtually. I hope that you will come and we will host you personally, and that you woke up very early in Brazil to give this talk. And today she is going to talk about Sahara fertilized Amazon, not that much, exploring mineral dust sources for the Amazon basin since the mid-Holocene. So thank you very much again, and the podium is yours.
Hello, thank you, Nicolas. I'm really happy that I'm here. Finally, it's happening. We've been trying to do this meeting for a while now, and I'm really happy that we are able to do it today. So with this introduction, I will already jump into the presentation. So I will today tell the story of, well, how I thought I failed my master, but then I published in Nature. So it's a good story, and I love telling some stories. So stick with me, and we see the trajectory of this work. So basically, the first contact that I had with this topic, it was the reading about this kind of impact that the African dust could have in the demise of Caribbean coral reefs. So I was like, okay, African dust at the Caribbeans, and I was really interested with this teleconnection with these distance. And then from there, I started having some more contact with the dust, that how could it impact the environment, the ecosystems and society and the climate. And also I got to know the global dust sources. So here we can see in this picture, let me see if I can show it. Can you see it? No, but I think if I do it like this, you can see it, right? So here you can see that the main dust sources are basically the desert areas or arid zones. So for example, here the Saharan Desert, here Mongolian, and then deserts and others, and then Australia and so on. And here Namibia. And we also have the dust sinks where this dust is deposited, and basically it's the Atlantic Ocean, oceans in general, and then some continents. And as we know, the mineral dust plays an important paper role in both in the climate system and also in the maintenance of these ecosystems through the biogeochemical interactions of the macro and micronutrients that can fertilize both the ocean and the continents, for example, nitrogen and phosphorus. And then I also was reading a lot about within this topic of fertilization, about this one ecosystem that was constantly being cited, which is the Amazon forest. So why it was constantly cited? It's basically because we have the Amazon basin that was created by the depression of this Precambrian bedrock, and the basin soil is also made of some sedimentary layers, as you can see here in this part of the presentation, where you can see there is these layers of clay, which is this darker color over here, but then you have like a very thick layer of sand, which could be more than 13,000 feet thick. So because of that, and also because of other factors, because it's a very old soil, we have a very soil that's very poor in nutrients. So basically, the source of nutrients to the Amazon forest can be divided into two parts. So the first one, let me see if I can click it. Okay, I would change it to this. Okay, so here, so the first one would be the dead plants and the recycling that's happening on the top of the soil, also animal decomposition and others. And then you have the second source of nutrients that would be the dry and the wet deposition of nutrients that are being brought by the wind, by the precipitation, and so on. So to understand how this deposition could potentially affect the evolution of the Amazon forest, as we've been seeing regarding the African dust and the Amazon, and how people were doing some assumptions that this input of nutrients could impact the evolution of the forest itself. Then we had to go back in the past to understand how these changes could impact and how this could be in the future if some changes are observed in these dynamics. So when I was reading about this, I also saw this presentation like very often about how the African dust is impacting the Amazon basin, and this is a video from NASA, so it's like really common to be cited. And also we have some works that they would say that even something more like more, how can I say, more dramatic, of like the Baudelaire depression, which is like in the Chad country, a single spot in the Sahara that provides most of the mineral dust to the Amazon forest. So by reading all these papers and by seeing these videos from NASA and so on, I started my master back in 2014 with two questions, basically. Can we find the Sahara geochemical signal in the Amazon soils? This was the first question. And then the second question was how the Sahara dust deposition varied during the Holocene. Because if we remember, I don't know if you're familiar with the topic, but from the early Holocene to the present, we had some changes in conditions in the intertropical convergence zone, and therefore the monsoon and all the precipitation that comes to the southern oh my God, the Southern America. Why did I forget these words? But anyways, so we know that from the early to the present, we had the problem with these. First, we had this Amazon dry phase, which corresponded to the Sahara humid phase, and also which is also known about the African humid period. And then after the mid-Holocene, we had the change in these conditions, and then that's why we imagine that this variation of dust would happen during the Holocene. So to try to figure out if we do have these, we were doing some dust composition and mineralogy methodology that they are used as reliable proxies for atmospheric circulation and also dust emitting sources. And how this work is it's really interesting. So we have both of these radiogenic isotopes, which are the strontium and the neodymium. And we know that by using these kind of diagrams, by analyzing these isotopes in some dust or sediments and so on, we can observe some of domains. So for example, if you have some juvenile sources, so for example, volcanic soil, we have these very high neodymium, while the strontium is really low. And at the same time, if you have very old soils, like reworked soils, in this case, for example, the Amazon soil itself, or the Sahara Desert, for example, we would have very low neodymium, and then we would have like higher proportions of the strontium isotopes. So we can see here, for example, in the right slide, figure, I will use it here, that we can see that if we can like come up with a database where we can put all the potential dust sources. So here, for example, Southern South America, we have this big domain over here, and then we have here like Vantage Hills and Frontier Mountains and so on. So we can see that different kind of soils which have different geological history, they would have different domains as well. So by using this kind of approach, we can use like it would be like a dust DNA. Once you have a segment and you do this analysis, you would know where these what kind of environment this dust comes from. And this kind of methodology, it's used as a conservative fingerprints for sediments and dust commonly to try to trace this provenance since the Pleistocene, Holocene, and also modern time scales as well. Okay, so first thing that we needed to do before we started the work with the past was trying to understand how it was the dust influx in the present. So we would know how to calibrate our information in the past. So for that, I used two methods, which was the high split, which is this tool that's made by NOAA, which allow us to trace and to model air mass trajectories, in my case, backward air mass trajectories. So for my case, I would put the destination point as the Amazon forest, and then I would model how was the air mass trajectories that were arriving at this point through time. And also I use the outgoing long wave radiation data. So I could, by using some old codes like Fortranos and stuff like this, very old codes language, we would try to trace the position of the intertropical convergence zone, since we know that this could impact the air mass trajectories pathways. So in this video that I will show you right now, you see that how it was the dynamic of the intertropical convergence zone influencing the position of the trajectories of the air masses arriving at the Amazon. So you can see here the Amazon, then in blue the intertropical convergence zone, and we know that during the Northern Hemisphere summer, when the intertropical convergence zone is in the north, most of the backward trajectories comes from the north. And then when it moves back to the south, in the Southern Hemisphere summer, all these trajectories, they come from the Southern Hemisphere mostly. And you also have some moments like this one that we're seeing now, where we have mixed sources, when is the transition, usually spring and fall. So you can see here that we have coming straight from the Northern Hemisphere, from the Sahara region. We also have here, when it comes from the Southern South America, and from the Northern Africa. We also have moments when it's peak of the summer here in the Southern Hemisphere, where you have all the sources coming from Southern Hemisphere sources, for example, the Southern Africa and the Southern America. So you see that the position of these of the intertropical convergence zone really affects where this dust is coming from, or at least where it has the potential to arrive by having this direct pathway to the Amazon. And here in these graphs, you can see the sum up of what we saw in the little video there. And with that information, I could see which were the potential dust sources. So you can see some dots over here. These dots were all the places where I got some segment samples, and then we had the radiogenic isotopes analyzed in these samples. So I could put up this graph over here, where the one that we showed earlier, where you can see the different domains. So for example, Sahara Sahel, it's basically this purple part over here. I will use this, so around here, for example. And we do have some more juvenile sources, for example, the Central Volcanic Zone in South America. We also have here, for example, the Southern Volcanic Zone and the Austral Volcanic Zone. So as I said, all soils here, down and low in neodymium and high in strontium, and while the volcanic soils are the opposite. So let me come back to here. So to calibrate this in the present, we have used these samples coming from this tower over here. I don't know if you know about it, but it's really interesting. Is this 300 meters high tower in the middle of the Amazon, which is called the Amazon Tau Tower Observatory, which is basically for science. So they did have this collection of aerosols filters over there. So I got a collaborator that got these filters for me. And by having the data of the, not the data, but the date of when these filters were collected, I modeled the aerosol index for that moment. So you can see here that we have some dust emitting sources in the moment of the collection of these samples. And I also modeled the Hermes backward trajectories as well. So in here, I also did the same kind of database that I showed before. And basically, this is the result. So in these gray lines over here, you can see the results of the sample. So we have one filter that was collected in January, and then the other filter was collected in September. And for the filter that was collected in January, you can see that we have the northern Africa, West Africa, emitting these dust, so Sahara-Sahel region, and we also have this pathway of the Hermes trajectories bringing these dust towards the Amazon, because of what we saw before, the intertropical convergence zone, and here's is the summer in the southern hemisphere and everything that we were talking about. So when we see the result, we can see that the neodymium amount that we found in this filter is related to the Sahara-Sahel component here. And at the same time, we can see a very interesting moment where we do have two sources emitting the dust, but then you can see that the trajectories only bring dust from the Southern Africa. And this also appears here in the neodymium content, where it's related to the Southern Africa emission sources and not with the Sahara-Sahel, although it's emitting. So this is really interesting. Is the first thing that we can see that it doesn't only need a dust emitting source, but also a pathway to bring this dust to the destination. And now with this understanding, we could go to the dust influx in the past. So here we were looking for a suitable lake in the Amazon basin that would have recorded this phenomenon in the past. And we can see that the heart of the Amazon basin is pretty much flat. So let me show you here with this figure. So you can see that's pretty much flat here where you see the green parts. And then we were looking for this lake, and we found Lake Pata, which is this lake over here in the black dot. And the position of Lake Pata is really privileged because it's basically in 0 degrees. So it records these conditions of the intertropical convergence zone as well. And here is the place of where we were working. So it's called Seis Lagos Hill, which is 6 Lakes Hill, basically, which is part of this Cretaceous carbonatite complex. And the sediments, they were intensively modified and reworked because of the weathering. And therefore, it was formed in this lateritic crust, which is rich in rare earth elements. Some lakes that they are like around 15 meters depth, for example. And as the name suggests, we have 6 of those lakes in this hill, and they are totally away from human activity and is pristine. Another thing that's interesting about this lake as well is that we have this closed basin, so it's not connected to any drainage system outside of the lake itself. So basically this lake, it's an isolated system that only receives material from these lateral inputs in the lake, and also by means of wet and dry deposition on the lake. So this means it's a really good lake to study some deposition of dust in the Amazon. So we have collected this sediment core, which is dated back to the 7,500 years old. and we analyzed all the strontium and the radiogenic isotopes in general in this segment core. So we also put up this database, and in this database you can see here these two pink dots over here is the signature of the crust, the laterite crust itself, because if we do have the influence of lateral input and then with this wet and dry deposition here, if we know the signal of the lateral input itself, we could isolate, or we could try to understand what is the signal that's coming from the atmosphere, and therefore we could understand this dust influx dynamics. So here we have the result, and as I said, these pink arrow here, they point out to this signature of the geology of the place itself. And we have here in red let me put here these, we have here in red the result of our sediment core. And the first thing that we can analyze is, first, if it was only the geological influence, we would have all these red dots either on top of the geological signature, the local geological signature, or in between those. And if we do have the Sahara Sahel as the major source, we would have these red dots moved towards the Sahara Sahel domain over here on the lower part of the graph. So this is the first thing that we can see. So as at this point, I said, okay, I will have to start all over again, my master, because everyone was saying that it could come from the Sahara mostly. So here's the sample, and then to try to untangle these sources, because it's really complicated to see just by looking at it, I came up with this method, which is called the binary mixing method. And I modeled some curves for different mixing hypotheses between the Seis Lagos hill crust and a type of isotopic domain, including the extremes and the average value of these domains. So here I was trying to understand, I'll put again this. So here in green, we have the Seis Lagos hill laterite. So if it was only the Seis Lagos hill, all the points would be here. But here you can see that the Lake Pata sediments are dislocated, as you can see here by the red dots. And then here we have the Argentinian loss domain, and here all the potential mixing curves that would be, for example, if I had 90% here, for example, 90% of Seis Lagos hill laterite, and then all the rest for the Argentinian lost, and so on. So here I have modeled it, and then I have the sum up of these results, which we can see here on the right. So different from most of the papers that we were seeing, the mixture between that came up the Lake Pata sediments, they are basically a mixture between the sediment that's local for the local geology, and 4 to 10% Sahara dust from the Sahara Sahel sector, 8 to 11% Bolivian and Peruvian soils, 10 to 50% the Southern Africa, and 13 to 15% the Argentinian loss, as we can see here in this graph. So this was the first answer for the question, can we find the Sahara geochemical signal in the Amazon soil? And the answer is yes, but not as much as they were thinking before. And here we can see this signal through during the early Holocene to the present, early to mid Holocene, basically. So we have to come up with some points here. So first thing that we saw before, that even if we have this dust being emitted by one place, if we don't have the pathway, the transport to it, it cannot reach this destination that we're thinking. So this leads us to the second question: how did Sahara dust deposition vary during the Holocene? So during this recorded period, we had this change in the climatic conditions, as I said before, especially regarding the intertropical convergence zone position. So during the early to mid Holocene, the ITC set had this northward position, and this of course had impacts on both the Amazon and the Sahara, leading to the Amazon dry phase and the African humid period, as I said before. So this scenario would cause a much drier recording in the Amazon, as we can see here in, let me see the color, is this green line over here, where we can see the isotopic record for the carbon-13 in the lake pattern. We can see here during this Amazon dry phase, drier conditions, as we can see here. And at the same time, the ITZ is displaced northward, so the dust flux is redirected to the northern hemisphere, and as we can see by the backward trajectories. And according to the literature, during this time, the South Atlantic high pressure zone was more active, which would favor these conditions for transport from sources located at the southern hemisphere. And at the same time, looking at the mid-Holocene, we can see a southward migration of the intertropical convergence zone, which causes a drier Sahara, and therefore would increase the Sahara dust flux to the Pata Lake. However, the Northern African neodymium signals, they were progressively being more negative, as we can see by this blue curve over here. And also in a more humid Amazon, we would expect higher input into the lake, lateral input. So as I showed earlier in this structural neodymium diagram, the hill crust itself is quite high in neodymium, and only more juvenile sources would make these. And we can see here the laterite crust neodymium is this gray shaded bar over here. So if it was only the laterite crust, it would be much closer to this gray part over here. But then you can see that within the time, all these deviation from the laterite crust were much more high in neodymium, which is probably related to an input of more juvenile sources, which is definitely not the northern Africa with Sahara and Sahel. And this coincides also with this number of eruptions in the mainly in the Chilean part of South America, which we can see much more higher volcanic eruptions, and therefore probably these would impact this neodymium signal over here. And one thing that I wanted to highlight here is that even if we look closely, the Sahara dust transport occurs during this Amazon wet season. So you can see by this blue shade here is the condition of the precipitation in the continent. And when we do have this transport of dust from the Sahara to the South America, it's exactly when we have the rain season, so the wet season. So this could mean that when the dust arrives at the continent, it gets washed out in the beginning of this trajectories through the continent, and then when it arrives to Western Amazon, for example, the western parts of the continent, it would probably, all the dust would probably be deposited before arriving at this part of the Amazon. So one thing that we have to also remember is that the Amazon basin cannot be considered as just one thing, because it's like huge. So the dynamics that occurs in the east part could not be necessarily the same in the western part of the basin itself. So to try to say something like the single spot that of dust that is important for the whole Amazon basin could be an exaggeration of these condition. So my conclusions here are basically that we do not rule out the Sahara dust as this important player, but probably this is not valid for the entire hydrological basin, because although we do have this residual fingerprint of the Sahara dust in the western part of the basin, other sources that were not cited before, such as the Southern African and the Argentinian loss, for example, seems to be more dominant for more continental and inland portions of the Amazon basin. And another thing that I want to stress out here is that I think this is the first more directly measure of these kind of fingerprinting and as in the Amazon itself, because most of the papers are almost everything is only related to the atmospheric conditions, and we know that all these conditions that are seen in the atmospheric and satellite data, it's related to the current, and we know that these conditions changes throughout the evolution of the Amazon itself. So we saw here that we have these results of combined sources that modulate not only by local and global climatic conditions, for example, the latitudinal shifts of the ITCZ, but also of the dynamics over the Southern Atlantic Ocean, for example, and also the conditions, the climatic conditions on top of the continent itself. So our data basically tells us that the Sahara dust influence over the Amazon basin is most likely geographically limited, as I said, and then this fertilizing issue cannot be generalized to the entire basin at the same way. So these kind of scenario pictures are much more complex multi-factor issue than that has to be analyzed in a much wider window of time and not only with satellite and atmospheric conditions of the present. So take-home message is basically three things. So what should be taken into consideration when postulating potential dust sources to the Amazon basin, but also to anywhere else? So first thing is that we have to observe these favorable conditions related to the atmospheric transport between this arid region where we have the dust being emitted and the central western Amazon as well. Second thing is the relative intensity of dust emission at the source, because we have to have a substantial amount of dust being emitted to be able to be transported and arrive at the destination far away from its source itself, but also the local climatic conditions at the deposition locality concerning the dust deposition, for example, with the wet removal during the transport and so on and so forth. So with that, I conclude my story, and I thank you very much, and I'm open for questions as well.
Thank you very much, Juliana. It was really enhancing our understanding on South America, which is a little bit far geographically. So really thank you. I open the podium for questions to the audience. Just pop in and ask a question, and don't be shy.
Hi, my name is Sasha. So I have just one question. Are you have plans to expand this research? I mean, to take not just Lake Plata, but another different lakes, because it's just one point, and could it be representative for all basin? You mentioned that we could expect, yes, different patterns of inputs along, but can we have you plans and about it?
Yeah, so this is the project that I have more that I'm more linked to. So I would love to have the second part of it. So far, so the challenges are basically first to find another suitable lake, because this lake was like an open air laboratory. Since it's all like pristine and isolated from the other basin, it was easier to get to know these mixture sources. So if we think about lakes in the low plain, for example, of the Amazon, which are much more frequent, it's much more complex, because we do have the rivers that sometimes they overflow to the lake and then it changes the composition. So this is the challenge. It's finding this suitable place. And the second thing is that we have to one thing that I learned, as you said, this is one point, one dot. So I cannot say that this is the dynamic for the entire hydrological basin, which was most of the conclusions that they were doing. They would see in the atmospheric satellite the dust, and they would say, oh, this impacts the whole Amazon. So this is something that I learned. I can only make these conclusions, not saying the whole Amazon, but saying this part, central western part of the Amazon, behaves like this. So I did have these, actually, I don't know if I put it in the slides itself. No, I didn't, because I had some few slides after the thank you very much, which exactly shows if I had all the money and time in the world, what I would do in the second part of the project to continue with that. So yeah, so far I've been trying to look from suitable lakes, and so far nothing. I had all the other 5 lakes that I had in this hill, but they do not record the Holocene. Only Pata Lake, specifically in one sector of Pata Lake, it has the amount of sedimentary a process that can allow me to have high resolution the Holocene. All the others, they don't. So it's a very good challenge, and I would love to find another lake to continue that.
Nice. It will be really good to have 2 points and compare it, and
Exactly.
even if it will be really close, because we need to find, not we, you need to find a really good system to.
Exactly.
Yes, thank you.
Thank you for the question.
Thank you very much. Somebody else has a question? Okay, Itze, go ahead.
Hi. First of all, thank you. It was a very good, very clear, very nice talk, and definitely teaching, because people were really giving too much credit to the Sahara. I assume that there is some record of the dust that was washed to the continental shelf, to the delta of the Amazon, right? And that dust is basically the wash away. It's the integral of the Amazon that is washed out and concentrates on the shelf. How do your results compare to those records?
Yeah, so for example, I was using some continental shelf data, for example, in these here, let me come back here. Here, oops. For example, here we have this ODP core over here, which records the neodymium variation.
You need to share. You're not sharing at the moment.
Sorry, just one second. I have to close these and come back here, sorry. Okay. I think now you can see it, maybe?
Yes.
Let me put this big over here. Okay. So here in this blue line over here, I did have consider the OTP dot. This core was made in the continental shelf in Africa, just in front of the Sahara. So I was trying to see how the neodymium signal was changing through the time. And I also tried to do the same using sediment cores from the Amazon itself. So in the Amazon shelf, or I don't know, in front of Ilha de Marajó, which is this island in the end of the Amazon River. But the problem is that I have the say of one of my professors to see how challenging is that to analyzing the continental shelf. So first thing is the resolution of the shelf itself, because we do have lower resolution when we take into consideration ocean sediment cores. But then the second part that he told me once, it was very illustrative. So he was telling me, I will ask you, what is the name of a food that when you make there in your country, it's really smelly, or like the smell is really strong? What's an example of food, any food that is like really strong, the smell is really strong? Because here in Brazil, we do have these very strong smelly food, and he was saying to try to find a fingerprint of Sahara dust in this continental shelf would be like trying to smell a very nice perfume when you're cooking this very smelly food. So the signal would not be sufficient for us to try to isolate it. So this is the challenge of trying to do fingerprinting in the continental shelf sediments for cores, for example. So in here, I don't know if you know about this food made of acarajé, which is really strong smell. So he gave me this example, and this is what happens. So we could do this signal, but you can see the dots, the resolution of these segment core over here in the Africa. And for the Amazon, it's even more complex because you have the whole signal of the Amazon with the rivers and tributaries and everything going
Hello?
Hi.
Okay, thank you. I think,
Did I
yeah,
got cut?
It was cut for a second.
Okay. So did you hear everything, or should I repeat
Yeah. No. Basically, I think that we heard everything.
Yeah.
Yes, thank you very much.
No
Thank
problem.
you. I have a last question, if possible.
Yes.
How the cores were dated?
It was dated with carbon 14.
Like what? Phytoliths, a bulk
No, the
sediment,
organic matter itself.
organic matter.
Yeah.
And there is no reservoir effect.
Not that I remember of.
Okay.
We did have this reservoir effect in another lake that I worked in the Sahara, because it's really close to it's like an open lagoon to the ocean, and there we do have, but in this one I don't remember having.
Okay, cool. Okay,
Thank you.
if there is no further questions, I think that I will thank you again, really very much.
Thank
And thank you.
Thank you very much for this invitation as well. My communication channels remain open. If you do have more questions that you didn't think now and you wanted to ask later, and also for collaborations, I'm open. If you want to explore more these kind of topic, I'm really open to it. As I said, I really enjoy working with this topic.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you very much.
Thank you.
Bye-bye.
Bye bye.
Thank you.